Video, we're going to wrap up section 6.2, growth and decay models, with a few examples here. Some good real-world examples. So here in example 4, population growth. Suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximately how many flies were in the original population? So here we don't have t sub 0. We're going to have to work backwards. And this is going to be a little more computational work. But we will still be using the y equals ce to the kt formula. And we have two initial conditions. On the second day, there were 100 flies. And on the fourth day, 300 flies. So the population's growing, follows an exponential model. We're going to figure out what C is and what K is. So let's start with the first initial condition. We plug in 100 for Y, and that's equal to CE raised to the 2K. And remember, in the other ones we were solving for C. So here we can divide both sides by e to the 2k. I'll write it on this side, e to the 2k, and that will divide out. Now when I write it over here, e to the 2k, in the denominator, we can rewrite as e to the negative 2k. Remember, bring it up to the numerator and we make that exponent negative. So that's 100 e to the negative 2k is equal to the constant c. And we are going to plug that into this same equation with the second initial condition. So I'll start that under here, switch over to blue. Our y value is now 300. 300 equals CE to the KT, but now we know that C is equal to this. 100 e to the negative 2k power times, and now we're going to have our e to the KT, e to the 4t. We plugged in the 4 for our, or no, it should be 4k, excuse me, 4k. We plugged 4 in for the t. The 300 went in for the y. This 4 went in for t. And remember, this 100 e to the negative 2k was our c value from the first part. So we have bases, like bases. And even right now, why don't we do it? Let's divide by 100. If we divide by 100, this is gone. 300 divided by 100 is 3. And that's equal to, here are like bases. When we have like bases that we are multiplying, we add the exponents. Negative 2k plus 4k is positive 2k. So let's take the natural log of each side. The ln of the left, the ln of the right will cancel with the natural or the exponential base. So now we have the natural log of 3 is equal to, the exponent drops down, 2k. And when we divide both sides by 2, the ln of 3 divided by 2 gives us a k value of approximately 0.5493. 5493. So let's see, what can I get rid of? Probably most of this. So in the first part we solved for C, now we just solved for K. So back to the original equation. Y equals CE to the KT. Okay, so now that we've found K, what we're going to do is go back with the original initial condition of 2, 100. We're going to put that back into our equation with our known K value now. Because at time 0, the height on the y-axis is going to be the same as C. If I plug a 0 in for time, that wipes out the numerator to a 0. E to the first, or e to the 0 is 1, so y is equal to C at time 0. So now that we have this K value, we can use the original initial condition. Y is 100. That's equal to C times e to this K value, 0.5493, times time 2. And that turns into 100 equals C times e raised to the power 1.0986. 1.0986. And just like earlier in the problem, I'm going to divide both sides by this exponential. E to that exponent's going to cancel out. And over here it'll be e to the 1.0986 in the denominator. Move it up and make it a negative exponent. E to the negative 1.0986 is equal to c. And if we throw that into the calculator, that's 100 times that exponential, we're going to get approximately 33. Remember, we're dealing with the original population of fruit flies here. Here's our exponential, our initial conditions. It's curving upward in an exponential manner. We sort of backed up and found out what our y-intercept was. At time 0, where were we on the y-axis? What was our starting population of fruit flies? Had to be right around 33. Okay, and example 5 is a business world model. 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units a month to 80,000 units per month. If the sales follow an exponential pattern of decline, what will the sales figure be after another 2 months? So they tell us right off the bat this is a proportional relationship. Y equals c e to the kt. And we have, once again, 2 initial conditions. This time we do have a time 0. We were selling at time 0 100,000 units a month. And then we dropped the advertising budget a little bit, and 4 months later we were down to 80,000 units per month. And we're trying to figure out what's going to happen 2 months after that. At time 6, month 6, what's going on with the sales? They're telling us it follows an exponential pattern of decline. We should expect it to be, well under 80,000 units. So, to the our equation and our initial condition. 100,000 is our y value. That's equal to c e raised to the k times t. T is 0, so that becomes e to the 0. E to the 0 is 1. Our c value is 100,000. Now we're going to plug that into the equation with our second initial condition. So the second initial condition has an 80,000 y value. That's equal to ce to the kt, or 100,000 e to the kt, and now our time is 4 to the 4k power. And let's see here. We can divide both sides by 100,000. 80,000 divided by 100,000 is 0.8 equals e to the 4k. And then we take the natural log of each side. The ln of 0.8 is equal to the ln of e cancels out. We have our 4k. And then when we divide both sides by 4, we're going to get a k value of approximately the ln of 0.8 divided by 4 is negative 0.50558. So we're going to sneak up here. I'll clear a little room. And we can rewrite our equation now as y equals the c value we found was 100,000. E raised to the k, which was negative 0.0558 t. And I erased those, we had 0, 100,000, 4, 80,000. We were trying to figure out when time is 6, what's going on with sales. So we're going to plug a 6 in for this t. Instead of rewriting that, I'll cross it out. And that we're going to multiply at time is 6. So we would punch that into the calculator, and you're going to get approximately 71,500 units. Which makes sense. We know we've stopped advertising. Our sales should be going downhill. It's a slight curve, but it is there, an exponential decay model. Okay, in the examples 2 through 5, you did not actually have to solve the differential equation y prime equals ky. This was done when we worked on Theorem 6.1. Theorem 6.1 tells us that this is a valid relationship. And since it was sort of built in, we didn't really need calculus or solving a differential equation to solve those previous examples. The next example demonstrates a problem whose solution involves the separation of variables technique. The example concerns Newton's law of cooling, which states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature surrounding it, the room temperature. So in Newton's law of cooling, it says let Y represent the temperature in Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. If the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer will it take to decrease another 10 degrees down to 80 degrees? This one's going to take a little while. Don't write too big on your notes. So the rate of change of the temperature, delta Y or Y prime, is proportional to the difference between Y and 60, the room temperature. So the rate of change, Y prime, is equal to the proportional constant to the difference between the object's temperature and the room's temperature. Remember, we're using Y for our object's temperature, and we're in a room of a constant 60 degrees. So the rate of change is proportional to the difference between the object's temperature and the room temperature. And I'm going to rewrite dy, or Y prime, as dy dt, and that's equal to k times y minus 60. And let's see here, I want to get the y variable with the dy, so I would divide both sides by this parenthesis, and then I would multiply both sides by this dt. Let's do that first. If I multiply both sides by dt, that dt is going to wind up over here, and then I would divide both sides by the parentheses. dy over the quantity y minus 60 is equal to k times dt. So the variables are separated. K is just a number. Over here we have our y's and our dy's. So let's integrate both sides. So when we integrate over here, we have a function in the denominator. The derivative is its numerator. So that is going to be the natural log of the absolute value of the denominator, y minus 60. On the other side, when we integrate k with respect to t, we're going to get kt plus an arbitrary constant, c1. And at this point, we know the room temperature is 60. The temperature of our object is more than that, and it is cooling. So we can disregard the absolute value bars, because we know that y minus 60 is going to be a positive value. So let's drop the absolute value bars. Let's see here. What are we going to do next? Exponentiate both sides. So when we exponentiate both sides, we'll have our, let me change to red here. We're going to base e this side. This is now our exponent. And we're going to base e, so this is now our exponent 2. E raised to the natural log, those cancel, so we're left with our y minus 60. And on this side, let's even break this up. We have an exponential that's added together. Remember, when we multiply like bases, we add exponents, so we can separate this into e to the kt power times e to the c sub 1 power. And remember, e to the c sub 1, e is just a number, c is just an arbitrary constant, so e raised to some arbitrary constant, this will become an arbitrary constant, c. So y minus 60 is equal to c to the e raised to the kt power. What are we going to do next here? Let's plug in our initial condition and solve for c. Our initial condition is at time 0, the temperature of the object was 100 degrees. So for y, we put in a 100. That becomes 100 minus 60 equals c e raised to the exponent k times t, or k times 0, which is 0. E to the 0 is 1, so that just becomes a 1. So c is equal to 100 minus 60, or 40. So we have c is equal to 40. And we can rewrite our formula now. Now that we know that c is equal to 40, we can write our equation as y equals 60. Remember, we had y minus 60. We add 60 to both sides. Y equals 60 plus the constant we found, 40, e to the kt power. Now we're going to use our second given condition. It is cooled to 90 degrees in 10 minutes. So now time is 10, temperature is 90. So our y value is 90, and that is equal to 60 plus our 40, e to the, now 10 is our t, so 10k. When I look across all these terms, I see 3 of them separated by an equal sign. Why don't we divide through by a 10? So we could wipe all these out. Those 10s are now gone. And we're going to have 9 equals 6 plus 4, e to the 10k. Let's subtract 6 from each side. So we're going to have 3 equals 4e to the 10k. And let's divide by 4. 3/4 equals e to the 10k. So now that we have the right side down to just the base e, we can take the natural log of both sides. So when we natural log, we're going to have the ln of 3/4, which is just a number, and the ln of base e cancels, and we have 10k. And then we divide by 10 or multiply by a tenth. So we're going to have k equals, and that looks better, maybe a 1/10 ln of 3 to the 4th, or 3/4. Or you could do ln of 3/4 all divided by 10 in your handy calculator. That is approximately negative 0.02877. 0.02877. So we can now rewrite our model. Y equals, we had our 60 plus ce to the kt. We found our c was 40. Our base e is there. And now we have our k value as 0.02877 negative times t. So we found the model that we can actually use to answer the question. How much longer will it take to get the temperature down to 80 degrees? So what we're doing is, how much longer, T is what, to get the temperature down to 80 degrees. So we're going to plug 80 in for our y. 80 goes in for y. That's equal to 60 plus 40 e to the negative 0.02877 t power. And we want to solve for t. So first, subtract 60 from each side. This becomes a 20. Now that it's a 20, we're going to divide by 40. 20 divided by 40 is a half. So we're going to have a half equals e to the negative 0.02877 t. And now that we have it down to our base e, we're going to natural log. The ln of a half is equal to the ln here. We'll cancel with the e. Negative 0.02877 t. And when we divide the natural log of a half by that negative decimal, we're going to get t is approximately 24.09 minutes. So is that the answer to the question? Is that how much longer it takes to get down to 80 degrees? Be careful on a multiple choice test. On the AP test, that would be, if it was multiple choice, that would be one of the decoy answers, 24.09 minutes. Remember, when we started, at time 0 it was 100. At time 10 it was 90. They said approximately how much longer would it take to get down to 80 degrees. We know that this would be, let me do this, 24.09 minutes got us down to 80 degrees, but the question was worded, how much longer will it take to get to 80? So how much longer is the difference between 10 and 24.09? So it's going to require approximately 14.09 more minutes to cool down to 80 degrees. Always watch the wording on those problems. That's a real subtle difference. Could be an easy mistake to make on a test.